Hi, I'm Kai. So I'm a visiting PhD student from City Science. I'm so happy to share with you some use case of agent-based model. I work with City Science team this year, and this project showcases the application of ABM in different scale. I have three use cases here. The first one, algorithmic zoning will build a ABM model in urban system level to simulate a new mechanism of zoning. And the community simulator is a model to study the human event interaction in community level, and design exploration is a street level ABM like we are building with vision large language model. So first of all, we are trying to building an incentive behavior change through dynamic land use regulations. Like briefly looking back to the human settlements, in the early period of human settlement, housing was really simple. Like a family needed a home, so they built one with their own hands. As in the human people gathering, a tribe was formed, and through coordination and compromise to meet the need of different individuals, and a certain regulation emerged. Like people decide building the larger of the higher class in the center, and the defense housing in the edge. And as the settlements expand, especially after the industrial revolution, cities become more and more complex systems, and urban planning evolves into city sciences, which we are starting now. And there are some key period in this time, like in 1898, Harvard introduced the concept of the garden city, which marking the early exploration of regional planning. And in 1926, the U.S. Supreme Court upheld the constitutionality of zoning. Related to the zoning, the practice of zoning we know today, like this map in the right is the zoning map of Cambridge now. But is this zoning really what we need? As the system goes more and more complex, it seems like we are going further and further from the simple logic that we build what we need. For example, do we really want to commute between the office and the home twice a day? Like this morning, I walk from apartment to the media lab, and it takes me 15 minutes, and I don't think I like it. But there's no affordable housing for me. Like I can just live in the campus. And do we really want to separate work, shopping, and leisure into different districts? And do we really want to limit housing options in areas with better job opportunities or public transportation transit? But as the system becomes more complex, it's just like I want to build this and I can build it. We have different interests of groups in the cities. Like for the residents might want more affordable housing near jobs and need amenities in a walkable distance and increased wealth. But also they have their own concerns, like many of the residents may resist changes. They fear the negative impact of the newly development in their neighborhood. And for the developer, they are chasing higher density for making more money, and their main concerns will be return on the investment. And for the government, they want to increase revenue and a more engaged population. But can we have a win-win scenario, like everyone be happy? So to study this, we introduced a new zoning mechanism to incentivize behavior change, and an agent-based model to test and simulate the incentive policy. Like we want to test different incentive policies to encourage people change their behavior, which in the zoning process we are acting now. So in this model, we have three rows, and you can see here, like list in the white is the typical behavior we already have now in the zoning process, and the green items is changing behaviors from which is different from the typical zoning process. So first of all, in this module, every resident will have different profile, and different profile have different weights on the needs of different amenities, and a demand gap of each residents are calculated in a 15-minute life cycle, and the resident can decide the maximum density of a local project. And also, residents can get financial benefits from increased density through community endowment, which will encourage the residents to receive the changing of the community. And for the developer, we have a demand list of all local residents are connected for each project, and the developer can get reward density according to the incentive policy. And different incentives are calculated just over time according to the demand list. Developer can choose assets and amenities to develop according to results bonus and max density. And part of the increased profit returned to the residents through community endowment. By this way, the developer will be happy to build what the residents need in this community, and the community will be happy to build a higher density in this community because they can get the direct return of the profit. Also, for the government, they can evaluate the performance for the community through index system, and they can set and test different incentive policy using our platform. So this is a showcase of this event model. So when we initiate a project, first of all, we'll generate the different residents in this area based on the census data, and we can calculate what these agents around this project, what they need, and based on the demand list and the incentive policy created by the government, the developer will always chasing what benefits them most to define which project they want to build and what kind of amenities they will build in this area. And by simulate this process, yeah, we can see like in the total area, the demand gap of the residents will gradually fulfill with the time goes by, and the endowment of each household they can get will increase. And this is like a game-changing system of the zoning process, and this is one of the applications of agent-based model. Then the second use case is a community simulator. So we want to explore different community development strategies through a graph retrieval augmented large language models. This project specifically, we are studying the NICE community. This community is located in Shanghai, and it's built by Shanghai City Science Lab. And during this developing process, we want to know how can we learn the impact of different strategies during the community developing process. So can we build a community simulator to test different strategies? And to build this community simulator, we need to know how would the community members interact with each other and with new events. This is like human interaction and human events interaction. So first of all, we collect the human event interaction data during the developing process, like from 2020 to 2023. You can see this graph, like each node is an event. Like the purple node there is a long-term project, and you can see the connections of these different events and the people, and how different events can make connection with people and create more connection between people. So the community graph is constructed by two different nodes, actors and events. And actors is the residents in the community, and the events, they have three different categories, like medium connect, short-term project, and the long-term project. And the interaction between people and events, we have two types. The first one is A contributes to B, which means a person, an actor, is create the event B, and the A participate in B, which means the actor A participate in this event B. He is interested in this event. So then we create a community index system to evaluate the vibrancy and the creativity in this community. We want to know if the community become more vibrant with different events happen in the community, and we want to know if the community become more creative with different projects or different events happen in the community, and that the community has a broader contribution. So we use these three index, like average connection intensity, contribution, participation ratio, and the median contribution proportion to calculate this creativity and vibrancy. And the next step is the most important one, is to build a community simulator to test different building strategy in community. And there's several challenges to build a community simulator. We summarize as the 4U challenges. First of all, unquantifiable strategies are often very difficult to quantify. Like you can't define, sometimes it's hard to define the strategy as rules because it's hard. And a second, reliable data availability, like as Alan said, it's very hard to get all the data, like how humans interact with different events and how humans interact with each other. It might cause like privacy issues and other issues. And then the human behavior is not a certain rules you can define. Like today I want to have a Chinese food, and tomorrow I don't like Chinese food. So human behavior have their own uncertainty in this simulator and this simulation process. And last but not least, unique of community. Not like the general simulation of human behavior. Like in a city scale, we don't care about what a particular group of people they might do, but in community, like the study goal of us is focused on a very small group of people. These 15 people might act totally different from that 100 people. So it's caused difficult to simulate the uniqueness of different community. Some related work of community simulator, they all have their own limitations facing these challenges. And the most state-of-art work like generative agents, which means like humanized agents we're talking about, they have the potential to mimic human choice, but like the local context, because large models, they are training on a mass data set, and we only want to understand how these 50 people, what they want to do in this community. So we propose a new methodology by combining generative agents with graph RAG to provide the local context to the large model. And this framework will have 3 steps. The first step is, like I said, we have already built the data set of our community, and the first step is find similar people with agents in the data sets. So we have these 2 kind of similarity research functions. The first of all is the profile similarity, and the second of is the social similarity, which is calculated by graph structure, which the position of agents in this community graph. And secondly, we are using the graph recommendation to gauge the behavior based on what similar people would do. Like we use a link prediction algorithm to calculate the different choice of the agent might take. Like in this graph, this orange node is the new agent. We want to predict what this agent will do in this community. And the green node is the data we already have. And this green node link with the orange node means they are similar to this agent. Either they have similar profile or they have similar social identity. So using this link prediction, we can calculate different weights of this orange node. How would they choose the different other choice? We can calculate a weight on different choice, and we can get a recommendation. And the third step is to provide the context to get the final choice. First of all, we have different agents. We want to know what these agents will behave in this community. And when a new event happened, we can get, first of all, we can get the context from the community graph we built, and using the larger model to predict what this agent will react to this event. And once this behavior was generated, we can use this behavior to update our community graph. So this is an updating system which we have dynamic behavior. There's a question related to this is a static behavior or a dynamic behavior. So using this kind of structure, the behavior of the agents is keep evolving during the simulation process. And these are the results of our experiments. As you can see, the tendency is like this light blue line is the ground truth, and the dashed line is our simulation. And you can see in the raw data, the tendency is very similar through periods, but As the larger model, I think because the companies are trying to avoid the negative aspect in the larger model, so the model are more optimized on contribution than reality. So we use the normalized data to do the further analysis. And this is visualization of different community graph during process. But as you can see, like as the simulation periods increase, simulation community tend to repeat patterns because we can't actually simulate what truly happened in the community as the simulator goes further and further from the ground truth. And using this model, we can test different strategies like what-if scenarios. What if we never introduce long-term project to the community in the beginning? And you can see, as shown in these plots, we can see that long-term project has the greatest impact on contribution. So this plot is the contribution in the community, and this plot is like the connection in density in this community. So when we remove the long-term project, we can see the contribution this community decrease a lot, which means long-term projects actually can help the community to be more creative. And also when we remove the long-term project and the connection between people is decreased too. But what's interesting is like we test the second scenario, what if we never invite bloggers and encourage the creation of media content in the community, and we can find that the media content also have a great impact on contribution in the community, but when we remove the media contact, actually people become more closer because the connection between people increased a lot. That's much because when we reduce the virtual connections, more physical connection happen in this community, so people become more closer. And the third use case is design exploration. So we want to simulate human-environment interaction using generative AI and the vision large model agent. Again, like in a micro simulation, like what Alan did, we are trying to simplify the behavior of people to like as the direction line moving from one point to another point. But in a macro level, we want to know more detailed factors like such as trees, lightings, and colors, and how they affect human emotions and behaviors. In this way, we cannot just use a simple line guidance to move the agent because it's too simple. So, as many of you might know, this immerse scope demo, City Science team created this immerse space to allow users to explore different imagination of cities and get feedback from the participation and how they react to this virtual environment. So we want to move a step further. Using embodied intelligence interact with a human environment, so we can have a fabricated playground environment to simulate how people will feel and behave in different design space. So in this demo, users can use the design prompt to change the environment, like adding more trees or change the texture or change the weather or lights in the design space. And they can assign different tasks for the vision large model agent to simulate how people will react with the design space. So you can also use the agent dialogue to ask the agent, how you feel about the environment. And this is our baseline 3D model. Like this is a very simple experiments with some buildings and a cross street. And this demo this is our demo. Like the image upper is the 3D model. We render it as a segment map, and you see the stable diffusion to render different designs for this experiment. And typically this is a summer. The time is a summer, and you can see the agents can choose the directions they want to take, like moving forward or turn left or turn right to achieve the task. So we didn't assign any routines for these agents the agents can decide whatever they want to go and to finish this task, and we can have a dialogue to ask the agent what they feel about this environment. And the second, yeah. This is a changing condition, like what people behave in winter. You can see, like in winter, the agents will move more closely to the buildings and take a shorter distance to achieve the goals. Yeah, this is the end of my presentation. Thank you.